So far, we've talked about some of the key distinguishing features of the quantities that appear in mathematical models, and also the distinguishing features of the equations that make up the models themselves. In this lecture, we're going to talk about some of the features of model solutions and how we classify different types of model solutions. So we use the term solution in two different ways. In this class, the term solution can mean the method for solving a model to find the values for the model outputs, that is, the dependent variables, and it can also mean the result of applying that method, that is, the values of the model outputs themselves, or the values of the dependent variables. Solutions can be analytical or numerical. They can be what we call exact or approximate, and they can be what we call dimensional or dimensionless. So we'll talk about each of these three different ways of classifying model solutions. Analytical solutions can be found when the model equations can be written explicitly for dependent variables and solved directly. An analytical solution is one that we can write a mathematical expression for, representing how the dependent variable depends upon the parameters and the independent variables. Analytical solutions may not be the most convenient form for models that contain a large number of equations and variables. Numerical solutions, on the other hand, rely on computational iterative techniques to discover what the values are for the dependent variables. They may be required for implicit model equations that cannot be reformulated into explicit models with analytical solutions. Numerical solutions may also be preferred even for explicit models that have analytical solutions, particularly when the models contain a large number of equations and variables. Exact solutions are found when we have an analytical solution that can be found directly to a model, or when we have a numerical solution that has a known error bound and convergence criteria. If we have a known error bound and convergence criteria, then we can say that we know the solution of the model to within certain tolerance. We refer to a solution as approximate in a case when we're using a numerical method for which we do not have known absolute error bounds. So in the case of finding an approximate solution, we actually don't know how close our solution is to the exact solution. We also refer to approximate solutions when we make approximations to the model equations so that we can facilitate finding a solution. When those approximations lead to an analytical exact solution, we have an analytical or exact solution to our approximate model, which we use as a surrogate for our approximate solution to the full model. When discussing exact and approximate solutions to a model, we should remember that all models are abstractions, and no model results in an exact representation of a real process. Exact in this context only describes the relationship between the solution and the model. It does not describe the relationship between the solution and the real thing that the model is describing. All models are approximations of reality. One particularly useful tool that we will frequently apply when finding solutions to model equations is the Taylor series expansion. We will revisit the Taylor series over and over again throughout this course because it is the foundation upon which we build many of the numerical methods that we will introduce in this class. If our dependent variable y is a function of the independent variable x, and we know the value of that function at a particular xa, then we can approximate y in the region of xa using a Taylor series expansion. As I just said, this forms the theoretical basis for many of the numerical techniques that we'll study in this class. Notice that when we apply the Taylor series expansion, this converts any differentiable function into a polynomial. Two key ideas here. One is that f must be differentiable in the region of xa, our known solution. We have to be able to find the first derivative of f at xa, the second derivative of f at xa, the third derivative of f at xa, and however many other derivatives we want to include before truncating the Taylor series. Once we've found those derivatives and we substitute xa into those derivatives, then each of these terms in the square brackets simply becomes a constant. It's the result of evaluating the derivative of f at xa, or a higher order derivative of f at xa divided by a factorial term. Since we already know f at xa, its derivative at xa, its second derivative at xa, and its higher derivatives at xa. And we know what xa is. This expression is simply a polynomial in x. We have an x to the 0 term, an x term, an x squared term, an x cubed term, etc. Polynomials are very easy and straightforward to compute. Remember that we need to be able to differentiate at the point xa and to find values for the derivatives in order to use this technique.